Good morning. This is the video for section 3.1. You should have already read the first part of it and done a few exercises. I'm going to kind of talk through the entirety of 3.1 today, and then you'll have another assignment at the end. Let me say it off the bat. I'm also going to post another video shortly, a real short one. On these calculators, there is one setting that has to be changed once in order for it to do what we want. And some of your calculators probably have it correct and some don't. So there'll be a short video on how to do that also. That way, just you never have to do it again. Don't have to memorize anything, just to follow the certain steps to get something turned on that need to be turned on. So that will also be coming. All right. So we're talking about, this is chapter 3, which is, we're talking about describing relationships. And so 3.1 is scatter plots. You guys have been plotting data for years. So obviously you know how to plot an ordered pair. As far as just some of the terminology goes, you should, let's see, let me get the pen going here. You need to be okay with response variable and explanatory variable. So you need to know that I like this paragraph. No, not here. Let me get me out of the way here. This paragraph here, you may have heard them as independent and dependent variable. That's not wrong. But statistically, and we talk about two events being independent, that has different statistical meaning. So you won't see it used here, but nothing wrong with really using it. This is the X, this is the Y. You have to know that the X is the independent variable, which is the explanatory variable. Those are interchangeable. And then the Y, which is the dependent variable, is the response variable. You just have to be able to identify which one's which. So I know a couple of your exercises just ask, hey, in this scenario, which one would be which? In many cases, it should be clear. If I just give you ordered pairs with no context, it would be X is explanatory, Y is response. But if I'm just measuring two quantities that happen to have no relationship, like what's your favorite number and what's the number of screwdrivers you have in your garage, and I just kind of randomly make ordered pairs, it's okay in a case like that for there not to be necessarily an independent, dependent, or explanatory response. But in most cases, it's obvious, or you should be able to figure out which one is which. Okay, so that's just that. We're kind of scroll through what you should have read here. That just has you talk about which one is which, so we're good there. We'll go to the next page here. Okay, so now displaying data in a scatter plot. Your assignment did have you make a few scatter plots, or at least one by hand. The AP test won't have you do something with any intricacy where you have to take a lot of time to do it. It may have you make a simple one. The calculator will also make a scatter plot for you. I will also put a video on how to do that, like where to put the data and how to turn it on. We'll get to that. Not needed for this conversation, but you know what a scatter plot is. So obviously, if you're going to sketch a scatter plot on your AP test or on my test, make sure you put the right variable in the right spot. Make sure you label stuff, and then each individual value has a data plot. So again, nothing surprising there. That's just how to make a scatter plot. Make one so that there it is. That's brilliant. Okay, nothing to that. I'm going to kind of quickly go through what you already read through, and then I'll take a little more time on the newer stuff. All right. Okay, so now we're describing scatter plots, and this is important because you're often asked on my test, certainly, and on the AP test, describe a scatter. Here's a scatter plot. Describe it. You have to remember what you already know and not confuse with what I'm teaching you now. I gave you a distribution, just a single set of data, test scores, temperatures, whatever, and I asked you to describe that. You know that's SOX, shape, outlier, center, spread. I give you two distributions, like two different class sets of scores, and I say compare the distributions, you're still using SOX. You're talking about the shape of each one. Remember the outliers, the center, like you're going to say the mean of set 1, which is 42.8, is greater than the mean of set 2, which is 41.7. And then the spread also, range, IQR, standard deviation, whatever. Please remember when you're doing that, make sure somewhere in your description or comparison is the context. I need units or something in there. So that was describing a distribution. Now we're describing a scatter plot. So we've got four things again. There's not a friendly acronym, but you have to talk about the. Oh, gotta get a pen. You got to talk about the direction. Is it trending up or down? That's all that needs to be, and it's allowed to be trending not at all, but often it'll be either up or down. The form. Is it linear? At least kind of. It doesn't have to be a lot, but like, are they at least trending kind of like a line that fit the data well, or is it curved? Really, those we're not going to get more intricate than that. And many we're going to talk a lot specifically about linear relationships. But like this example, I believe it says is curved. Because again, the general trend here, if I were to just, the general trend is kind of curved. So I wouldn't call that the form in linear. I'd say that one is curved. So direction, this is trending negatively. Now, put in context. That means the higher percentage taking SAT scores leads to a lower mean math score. Like that, put it in context when you say it's trending downward. And then talk about the form. This one is curved. And the next one says talk about the strength. Like how strong is the relationship? And that is an incredibly vague thing to say. Like, is this relationship up here strong or weak? Is it kind of strong? Oh, sorry, I meant to just scroll up like this. Nope, not like that. I scroll up. There you go. So I'm going to read what it says here. The strength of the relationship in a scatter plot is determined by how closely the points follow a clear form. The overall relationship in Figure 3.2 is moderately strong. States with similar percents tend to have roughly similar mean SAT math scores. So, and it's obviously very strong if the points are really close to a line, or obviously spread out. You could say weak, but moderately strong. I think that's an example of moderately strong. And there's a whole bunch of these where moderately strong tends to be a reasonable thing to say. So now we're going to quantify that when we talk about correlation here in a minute. But just overall strength, strong versus weak. And then we're also looking for outliers. Now, again, you have to pay attention here. An outlier could be in either the X direction or the Y direction. And we'll talk about there's actually differences in how that affects things. We'll get to that. So in this case, I've even looked at what the paragraph says down there. Maybe that one and maybe that one. I don't know. Oh, and now I'm reading the paragraph. Two states stand out: West Virginia, 19501. That's that one, and Maine at 8746. Outliers because they fall outside the overall pattern. Good enough. So again, when you're describing a scatter plot, you have to remember direction, form, strength, outliers. Just make sure that shouldn't be. It won't be a difficult question, but it's really easy just to say, here's a scatter plot, describe, and you say, oh, higher SAT percentages lead to lower mean math scores, and that's great, but it's not all once. Just like when you're describing a set of test scores, you say everyone did great. That might be true, but the AP test once, shape, outlier, center, spread. Here, the AP test once, direction, form, strength, outliers. It's one of those things you kind of have to know. All right, so that is that one. Okay, now let's talk about positive association and negative association. That's just whether the data is trending upward or downward. Like as X gets bigger, if Y is getting bigger, it's trending up to the right. That's positive association. We're going to use the word correlation in a minute here, but just in general, that's positive association. And then two variables have negative association. This is getting a little technical. When above average values of one tend to accompany below average values of the other. So it's just trending down. And then it says, I like this. It says, of course, after the green box, it says, of course, not all relationships have a clear direction that we can describe as positive or negative. Nothing wrong with that. Okay, so let's see. We got a scatterplot here. Obviously, now you had to describe that. There go my light. Sorry. If you had to describe that, we got what? Direction, form, strength, and outliers. The direction is it's trending upward. Higher number of boats registered leads to higher manatees killed. The form is that I would call that clearly linear. The strength, I think that's pretty strong. That's a pretty strong relationship. And outliers, I would say there's none. Again, sometimes that's a little up for argument. Okay, so good enough. Again, we're not going to worry now about drawing a scatter plot with technology, but we will at some point soon. Again, I'll throw a video up on that also. Let's read this AP exam tip. If you're asked to make a scatter plot on a free response question, be sure to label and scale both axes. Even if you do it on your calculator to see what it looks like, then make a sketch, just make sure you're labeling the axes, because obviously the AP grader is not seeing what was on your calculator. Okay. Okay, so that's that. Okay, now let's talk about correlation. So in particular, now we're talking about how linear is a relationship. And we're able to quantify that. So, all right, so here's the definition of correlation. The correlation R, and actually I've often heard this, okay, and here it is over here. It says some people refer to R as the correlation coefficient. That's kind of the way I learned it. The correlation coefficient R measures the direction and strength of the linear relationship between two quantitative variables. Now we just kind of breeze right through this, but obviously they have to be quantitative. If I'm plotting like your favorite color and your shoe size, I can't make a scatter plot out of that. Correlation would make no sense. If I said, here's some data of everybody's shoe size and favorite color, nothing wrong with that data. But if I said that data has a correlation of 0.3, you've got to know that makes no sense. Okay, so the correlation measures the direction and strength. So there are properties of correlation that you have to know what numbers make sense and what it represents, and then we'll worry about how to calculate it. So let me highlight a couple things here. Correlation is always between -1 and 1. The sign of R, whether it's negative or positive, that just shows whether it's negative association. So if I just draw, where'd my pen go? If I just draw that, R is going to be negative. And if I draw, I guess I could have done that. If I draw it like this, where at least the trending is upward, R would be positive. That's the first thing you have to know about correlation. And then it says, now I'm right here in this paragraph. It says the strength of the linear relationship increases as R moves away from 0 towards -1 or 1. Tell you what, let me go over to my smart notes, might make this easier. Let me go here and here. So we said that -1 has to be less than R, has to be less than 1. Like R can only be between -1 and 1. If you ever read that the correlation coefficient is 2.9, you've got to know that makes no sense. And we already said if it's trending upward, it's positive. It's trending downward, it's negative. If R were to equal -1, that means it is completely negative, which means the data is absolutely on a straight line trending downward. So I'll tell you what, I'm going to go like this and I'm going to cheat so I can make let me do this. I'm going to do another one. I'm going to go down here also. I want to erase those lines in a second. But if I put dots here, like I'm trying to get those exactly on the line. And here I'm trying to get them exactly on the line. I didn't do great, but I came pretty close. Here's my point. Yeah, this is important that this makes sense here. Let me get rid of these lines now. So pretend for a moment that those are points and they are exactly linear. Both of those would have an R value of -1. Notice that R being -1 has nothing to do with how steep the line is. It's not a slope thing, other than the fact it's got to be sloping downward. It's real tempting to think steeper lines have negative correlations. Not true. If it's trending downward and it's perfectly linear, it's going to be -1. Now, in real life data, rarely is it -1. So actually, the way I've got those dots, they're not perfectly linear. They're pretty darn close. So I would say if I had to estimate what those were, there's probably like -0.98 or something like that, -0.99, like really close to -1. And then similarly, any data that is trending upward, again, if I go like this, the R is going to be positive. And again, I would say that one might be, I don't know, 0.7. It's hard to, you're not going to be asked to precisely say the correlation, but if I gave you that picture and I gave you this picture, those are supposed to be dots. And I said, which one had a higher correlation? You should know it's the one that's not steeper, the one that's closer to linear, which this one might be R equals 0.9. Again, positive is just trending upward. All right. So now we go back here. Nope, go back there. All right. So now we clear that. Nice. Go back there. So let's see. So here's some examples. Here's R equals 0. I'm looking at these 6 graphs here. R equals 0, really, there's no pattern whatsoever. Notice the second one here, it's trending downward, but barely, negative 0.3. Here, trending upward, maybe a little stronger, just a little, positive 0.5. Now this one here, now we're back to negative and getting a little stronger, negative 0.7. Notice this one, again, not that I ever make you actually precisely estimate, but this one is stronger than the last one. My gut would tell me that's not quite as high as 0.9, but that's actually fairly strong. That's 0.9. And even this next one would be 0.99. It's negative 0.99. So just be aware, between negative 1 and 1, closer to 1, closer to negative 1, closer to linear. All right. We don't need that right now. Okay, so now let's understand what it's asking us to do here. It is asking us to, this example is a good example. Interpret, because you have to be able to interpret a correlation. Okay, our earlier scatter plot of the average points per game, the number of wins for college football teams in the SEC is repeated at top right. For these data, R equals 0.936. A says interpret the value of this. So what can we say about R equal 0.936? You've got to know that and we'll go down to the solution here in a second. That is positive, and that's pretty darn strong, 0.936. And please, you'll always lose points on the AP test if you don't interpret things in context. So let's see how it answers part A. The correlation of 0.936 confirms what we see in the scatter plot. There is a strong positive linear relationship between points per game and wins in the SEC. There's the context. And then B says the point highlighted in red on the scatter plot is Mississippi. What effect, this is another thing, what effect does Mississippi have on the correlation? Like if that outlier were removed, would it change the correlation? Let's go up and find the graph and look for Mississippi. Let's see, sorry about that. I gotta find the points per game. So here it is. Okay, so I believe that's Mississippi. I gotta go back. Sorry, I'm gonna go back and find Mississippi's. Okay, so did it talk about, let's see, outlier. So Mississippi must be that one right there. Okay, so if I remove that, you've got to know the rest of the points are more linear. So if I remove, now, think about this. Oftentimes, by removing an outlier, it makes the rest of the points more linear. But don't just assume that blindly. If I've got a scatter plot here, and my outlier is out there, clearly the data is more linear if I remove an outlier. But what if the outlier is out here? I would argue that how linear is that data? I don't think it changes much. So just be aware that an outlier might be far away from the data. It may or may not significantly impact the correlation. And I'll come back again in the next section as well. Like an outlier doesn't always have to have significance in the data analysis. All right, let me go back here. Sorry about that. What effect did it have? Oh, I lied. It was I guessed wrong. That was the outlier. But again, if I take that away, the rest of the points are still more linear. So, okay, another example where that outlier would probably affect things a lot. Okay, as far as calculating the correlation coefficient, the AP Stats, there's a formula sheet, has lots of formulas, most of which you won't use because our calculator doesn't work for us, but you have to recognize the formula. So I'm gonna circle it. Absolutely don't need to memorize it. Don't need to use it to find the correlation. I will point out something here, that these two parts of this formula, those kind of look like z-score calculations, x minus x bar over the standard deviation of x. They are. So we're actually, in order to calculate R, we're standardizing some scores, and that's going to show up again in a minute. So don't need to do anything with that formula, just recognize it. I've seen an AP test question where it just gives you like a multiple choice. Which of these formulas is doing the right thing? And you have a formula sheet in front of you. It's kind of knowing to reference it. So that's all I will say about the formula for calculating R. I will show you in another video shortly how to find R with the calculator. I'm not doing that today. All right. Blah, 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 blah. Okay. One more very important section. It says facts about correlation. There are some facts and some easy misunderstandings about correlation that I need to highlight here. So, all right, first one. Let me go back to my pen. First one says that correlation makes no distinction between explanatory and response variable. Now, when you're plotting data, it's going to for sure matter which one you call which. But think about it. If I plot some points and it looks like this, and there's X and there's Y, and let's say R equals 0.87. If I were to just switch X and Y, just take every ordered pair and say 8,2, make it 2,8, it would now look like, I gotta make sure I do this right, a little below and then going, it would look like this. It would just, the whole thing would just shift a little bit that way. Like, for instance, if, make sure my picture is not great, I realize that. If this right here is the 0.6 comma 10, then this right there would be the 0.10 comma 6. Like if I just did that to every point. The graph looks different, but how linear the points are does not change. So you've got to know that by changing X and Y, by interchanging or switching X and Y, does not change the correlation. Okay. Okay, and then this said, number 2 says, because R uses the standardized values, like it actually finds z-scores for every number, it says R does not change when we change the units of measurements of X or Y or both. So if I've got data and it's inches and feet and I convert it to miles and feet, the numbers will be different, but how linear it is will not change. Just changing the units does not change correlation. Okay, next. The correlation of X itself, the correlation R itself has no units. It is 100% wrong to say the correlation coefficient is 0.7 meters. That is wrong and you will lose credit for it. The correlation is, it's like what it said, it is just a number. So use units lots of times when there are units. I would encourage you to, if you haven't yet, read this cartoon and just be amused by it. We're going to fly through it. All right. Okay. A few more facts about correlation. And we'll come back to this a lot as the year goes on. Correlation does not imply causation. If I have two quantities and there's a high correlation, it does not prove that one variable caused the other. There might be something else causing both of them to be very close to each other. Sometimes there is causation. We will do things eventually mathematically to show causation, but it's real tempting to think just because they're correlated that one caused the other. And it's not, and it's just not the case. So just be aware of that. All right. This one we already talked about. Correlation requires that both variables be quantitative. Again, if I have favorite color and salary, those are not both quantitative. If you say the correlation coefficient between favorite color and salary is 0.7, that also makes no sense whatsoever. So both variables have to be quantitative. Obviously, I can't make a scatter plot if I don't have quantitative data. All right. Next one. Correlation only measures the strength of a linear relationship. If the data looks like this, if the data is curved, now, can you put that scatter plot into a computer or a calculator and have it calculate R? Yes. That R wouldn't have much meaning. So correlation does not describe the curve relationship, no matter how strong it is. A correlation of 0 doesn't guarantee that there's no relationship, just that there's no linear relationship. And again, a lot of the things we're doing are with linear relationships. But if your data looks like a parabola, then finding the correlation coefficient really has very little meaning. And then again, this you got to be careful. This seems contradictory. It says a value, the last one, a value of -1 or close to -1 or 1 does not guarantee linear. A scatter plot with a clear curved form can have a correlation that's close. So the moral of the story is make sure you plot your data to justify or to back up. Here's an example where that's clearly curved, but it's close to 1. So just be aware. It's only talking about the strength of the linear relationship. All right. Okay. I forgot there were one more of these, but this is an important one. Like the mean and standard deviation, the correlation is not resistant, which means it is strongly affected by outlying observations. So when you have outliers, just make sure you're aware of them and what effect they might be having on the correlation coefficient. Okay. I think that might be it. Let me see what comes up next. I apologize. Yes, we're in fact done. Okay. So that's it for 31. Your assignment, like put this on the next page here. And again, it's in your Google Classroom assignment. I'm gonna put it here anyway. It is starting on, and this is really the end of 3-1. I'm going to put 2 calculator videos on also, either today or over the weekend. One, just the one setting we have to change, and one, how to make a scatter plot on the calculator, and actually also how to then calculate R, like the correlation coefficient, which you will do for us. So expect those. But you don't need those videos to do this assignment. So your assignment, starts on page, where'd it go? Page 150, 160. So we're on page 160, and you're doing 7 and 8, and you're doing 11 through 13, and you're doing 15 through 17, and then a set of multiple choice questions, which is 27 to 32. We'll make this due on Monday. So again, expect 2 more videos about the calculators, also 2 or 3. I'm not sure how I'll do it. All right, that's it. Have a great Friday.